G'day everyone, and welcome to our lesson on orbits and periods. When I was in school, we had a school camp, and as part of the school camp, since it was so far out in the bush, they made everyone lie down on the concrete and look up at the stars. And they promised us that if we lay there long enough, we'd see something interesting. And we actually did. We lay there for about 3 hours and we saw meteorites, which look a bit like that. And we also saw satellites, which look like small white dots that move across the sky. And our teacher told us that when he was younger, and the space race was just beginning, more and more of these white dots were filling up the sky, some of which were spy satellites, and some of which were telecommunication satellites. And in this lesson, we're going to discuss how, if you know how high that satellite is above the surface of the Earth, you can say exactly how long it takes to move around the Earth and how fast it's going, using our gravity force equations and circular motion equations. So let's represent this in a little bit of a more sophisticated fashion. I'll put down some key equations first. Okay. So with anything in orbit, the centripetal force has to be supplied by the gravitational force. The centripetal force is equal to mv squared on r, which is the same as 4 pi squared r m on t squared. This one being useful when you know the velocity, and this one being useful when you know the period. And that has to equal, I'll move this over, Fg, which is given by g m m on r squared, and g is the gravitational constant, 6.67 approximately, times 10 to the negative 11. So let's say we're modelling a satellite going around the Earth, and the satellite has mass, we'll say 100 kilograms, m equals 100, and the Earth has mass 5.97 times 10 to the 24. The radius, or we'll say actually the altitude of this satellite to the centre of the Earth is equal to, we'll set it as 370 kilometres. So 370, and straight away I'll go to metres, times 10 to the 3, times 10 to the 3 metres. There we go. The goal of this question is to work out the period. How long it takes this satellite here to make one full trip around the Earth in a perfect circle. So the first thing we need to do is line up our equation here. We know that there is some kind of gravity force affecting this satellite, and it's acting in this direction here, Fg. And we also know that the net force on this object, if it really is moving in a perfect circle, has to obey the circular motion formulae. And since we are looking for the period, let's use this formula. So the net force is 4 pi squared rm on t squared. And this has to be equal to the gravity force. So that's g m on r squared. The first challenge we need to complete is figuring out what is r here. So we know that altitude equals 370 times 10 to the 3 metres, but r is actually measured from the centre of one object to the centre of the other. So we've got to ask ourselves, what is the actual radius of the Earth? And that can be found, it'll be attached to these type of questions. The radius of the Earth is 6.37 times 10 to the 6. So little r here is made up of one of the radius of the Earth and the altitude of the satellite. So r is equal to a plus big R. That's 370 times 10 to the 3 plus 6.37 times 10 to the 6 that comes to 6.74 times 10 to the 6 meters. So we know the gravitational constant here, we know the mass of the satellite, we know the mass of the Earth, and we know R. So let's figure out F of G. F of G is equal to 6.67 times 10 to the negative 11 times 5.97 times 10 to the, whoops, I hope I said 24 over here, 24 times 100, all divided by 6.74 times 10 to the 6, and I have this coming down to 8.77 times 10 to the 2 newtons. So that is the gravitational force on this object here. Since this is the only force acting on the object, and we're assuming that it really is moving in a perfect circle, it must also obey this formula here. So R was equal to 6.74 times 10 to the 6, and now we use this formula here. We know that 4 pi squared Rm on t squared is equal to 8.77 times 10 to the 2. Therefore, t squared, moving that up here and this down here, so multiplying both sides by t squared and then dividing both sides by 8.77 times 10 to the 2, t squared is equal to 4 pi squared. Now instead of writing R, I'll write what R actually is, 6.74 times 10 to the 6 times m, which is 100, all over 8.77 times 10 to the 2. And I have this coming out as 3.04 times 10 to the 7, what's that, seconds squared. Therefore, t equals the square root of this side here. T equals the square root of that. Square root of 3.04 times 10 to the 7 seconds. Or seconds. Yeah, once you square root it, it'll come out as seconds, which equals 5.51 times 10 to the 3 seconds, which is around about equal to 90 minutes, which is the period of the ISS. So no matter, we'll prove that in a second. Basically, this satellite here is sitting at the same altitude to the ISS, around 370 times 10 to the 3 meters. Instead of working with real numbers now, we're going to try and work with the algebra to get a sense of what actually affects the altitude and the period. Okay, here we go. So, R equals A plus R. We'll use that. We know that the gravity force, Gmm on R squared, is equal to 4 pi squared Rm on t squared. We basically know the value of everything in this formula except for t squared, which is what we want to find. So we're going to try and get t squared by itself. The first thing we do is divide both sides by m and multiply both sides by r. So r squared here becomes r. Actually, sorry, we'll divide both sides by r. So that r disappears and this becomes r cubed. Whoops. Yeah, we also got rid of those m's there. Next, we'll multiply both sides by r cubed. So we have g m equals 4 pi squared r cubed on t squared. Now we multiply both sides by t squared, so t squared is equal to 4 pi squared r cubed gm. And now we divide both sides by gm, so we get t squared by itself is equal to 4 pi squared r cubed on gm. And this shows us that t is equal to the square root of 4 pi squared r cubed on GM. Let's see if this spits out the correct value that we had before. So t is equal to 4 pi squared doesn't change. R was equal to 6.74 times 10 to the 6 cubed. G is equal to 6.67 times 10 to the negative 11. And M is equal to 5.97 times 10 to the 24. So plugging this into the calculator. It's very easy to make mistakes, but as long as you use your brackets properly, things tend to work out. 4 pi squared times 6.74 times 10 to the 6 cubed Damn, got a syntax error. But when I calculated it before, it came out that t was again around about equal to 5.5 times 10 to the 3, which again is 90 minutes. So you can use this, if you can get into your calculator properly, as a shortcut to the answer rather than dealing with all these real numbers.